All right, we're gonna try this. See if we can go and do the whole review in one shot. Let's see if we can do this. Okay, so here's the Kinematics review. It says number one says to pass another car, Argo accelerated from 25 meters per second to 40 meters per second. 25 to 40 in 4 seconds. What's the acceleration? All right. Well, that sounds like a Vovat to me. So let's do that. So here we go. Here's number one. We're going to do a Vovat. Actually, let's draw a quick little picture here. So we're going from here to here, and we're accelerating from this speed to this speed. So here's my initial velocity. Here's my final velocity, and it all happens in 4 seconds. So it sounds like a Vovat. So my initial velocity is 25 meters per second. 25 should be an equal sign. So 25 meters per second. I'm going to try and go fast too, by the way. So please don't think that you need to go this fast in order to solve this stuff. I'm just doing this to limit the, yeah. So, okay, to get the acceleration, the acceleration is the change in velocity over the change in time. Once again, the acceleration is the final velocity, which is 40 minus the initial velocity, which is 25, divided by the change in time, which is 4 minus 0. And so my acceleration is going to be 40 minus 25, which is 15, divided by 4, which is 3.75 meters per second squared. And that is our answer. Awesome. And next we're going to get our displacement. So to get the displacement, I think I'm going to use d equals v naught t plus 1/2 a t squared. So to get the displacement, it's going to be my initial velocity, which is 25, times the time, which is 4, plus 1/2 times the acceleration, which I just found is 3.75, times the time, which is 4 squared. And if I plug all that in, I'll get 130 meters. And that's that right there. Awesome. There's number one. So, secondly, a commuter backs her car out of her garage with an acceleration of 1.4 meters per second squared. How long does it take her to reach a speed of 2 meters per second? So we're reaching a speed of 2 meters per second. All right. So once again, let's make this number 2 here. So I'm going to say is her car is from here to here. So here's her initial velocity. It's actually going to be 0. And then her final velocity is, what do we want? 2 meters per second. 2 meters per second. So we're reaching a final velocity. She's going to have some acceleration pointing in that direction. All right, so we're going to make a Vovat. Initial velocity this time is going to be 0. Final velocity we said is 2 meters per second. What else do we know? And her acceleration is 1.4 meters per second squared. And we're trying to find out how long it takes for her to do that. So let's see, I got that. I'm thinking the best bet is v equals v naught plus at. And then I'm going to isolate for the time. So it's going to be v minus v naught over a is equal to the time. So the final velocity is 2 minus 0 divided by the acceleration, which is 1.4 meters per second squared. So the time is going to be 2 divided by 1.4. So 2 divided by 1.4 is 1.43. 1.43 seconds. Is that what I'm getting? Yeah, 1.43 seconds. Looks good. If she then brakes to a stop in 0.08 seconds, what's her acceleration? So this is a new moment. This is a new moment. Now instead, she's moving at 2 meters per second. So she's moving. Now her initial velocity is 2 meters per second, and she's going to brake to a stop. So now her final velocity is 0. So, and then we're going to have an acceleration. So if we remember that Newton video, right? If we remember that Newton video, if she's moving to the right but slowing down, that means her acceleration has to be pointing to the left. If not, nicely enough, the math is going to tell us what is actually going to happen. So let's see, final velocity 0, initial velocity this time is 2 meters per second. Because she's moving now at 2 meters per second, she's coming to a stop. We're trying to find out what the acceleration is going to be, and what else? We know one more bit of information. What is it? Oh, she does it for 0.8 seconds. 0.8 seconds. So 0.8 seconds, we're trying to find out her acceleration. I think again I'm going to use v equals v naught plus at. But this time to get her acceleration, I'm going to isolate A. So v minus v naught over t equals the acceleration. V is 0, v naught is 2 divided by the time, which is 0.8. So 2 divided by 0.8 is 2.5. So the acceleration here is, and it's negative, by the way, because it's 0 minus 2. So negative 2.5 meters per second squared. That's that. Is that what I get? Negative 2.5. Nailed it. Next up, number 3, a bullet in a gun is accelerated from the firing chamber to the end of the barrel at an average rate of, okay, so this is the acceleration here, 6.2 times 10 to the 5 meters per second squared, and the person does it for 8.1 times 10 to the negative 4 seconds. So what is the bullet's muzzle velocity? That's the velocity it takes once it reaches the end of the gun. So let's see if we can figure this out. All right. I think I'm going to go even further to the right here. So boom, we got 3. So we got some gun. There you go. There be my gun. Green bullets. Why not? Green bullets. So there we go. We obviously know the initial velocity is going to be 0. What else do we know? Or what are we trying to find? So we know the acceleration is 6.2 times 10 to the 5. So it's accelerating. And let's also identify, this will be my displacement. That's the displacement. That's the distance right there. And we have an acceleration pointing this way as well. So let's make our VOVAT. We know the initial velocity is 0. Let's get the other information here. Acceleration is 6.2 times 10 to the 5. So it's going to be 6.2 times 10 to the 5, which seems like a lot, but remember, this is a gun. This is a bullet in a gun. So, and then next up we got 8.1 times 10 to the negative 4 seconds is how long it takes. So 8.1 times 10 to the negative 4, which also makes sense. It's a gun, right? It's a bullet in a gun, and we're trying to find out what the final speed is, what the final velocity is. So I'm thinking, again, we've been using it a lot, but let's keep using it. V equals V naught plus AT. So to get the final velocity then, the final velocity is going to be the initial velocity, which is 0, plus the acceleration, which is 6.2, times 10 to the 5, multiplied by the time, which is 8.1, times 10 to the negative 4. So the final velocity is going to be, 6.2 times 10 to the 5, multiplied by 8.1 times 10 to the negative 4, 502 meters per second. Is that what we're getting? Yes. And then lastly, how long is the barrel of the gun? Sounds like we're trying to find now the displacement. So I think I'm going to use the displacement is equal to the initial velocity times the time plus 1/2 AT squared. That's what I like about this is all I got to do is plug in stuff. So this is 0 multiplied by the time, which is 8.1 times 10 to the negative 4. But that's just all going to be 0 plus 1/2 times the acceleration, which is 6.2 times 10 to the 5 times the time, which is 8.1 times 10 to the negative 4. All this squared. And you should get, I'm just going to get the answer from this, you should get 20.3 centimeters, or let's say right at that meters, 0.203 meters, which is 20.3 centimeters, and that's what you should get for number 3. Hey, all right. Next up, hockey player skating at 17 meters per second comes to a complete stop. Whoop, that's a hint that the final velocity is equal to 0 in 2.3 meters. What is the acceleration of the hockey player? So let's go. So hockey player, this is number 4. Number 4, so at first the hockey player is moving. Let's say it looks like that. And then the hockey player comes to a complete stop. So the final velocity is going to be 0. There's some initial velocity though. That means then the acceleration has to be pointing to the left. So we can do a VOVAT. We know the final velocity is 0. The initial velocity is 17 meters per second. And the hockey player stops in 2.3 meters. And we're trying to find out what is the acceleration. Yes, we're trying to find out the acceleration. I'm thinking this one, v squared equals v naught squared plus 2ad, because I don't know the time, so I can use this to find out everything. And I'm trying to find out the acceleration, so it's going to be v squared minus v naught squared divided by 2 times d equals the acceleration. So plugging in numbers now, we're going to get 0 squared minus 17 squared divided by 2 times the displacement, which is 2.3. I'm going to get an acceleration of negative, because that's again 0 minus 17 squared, so 17 squared divided by 2 times 2.3, 62.8 meters per second squared. Boom! What do I get? 62.8? 63, sure, awesome. Okay, so next up, a car is traveling at 14 meters per second. So car is traveling at 14 meters per second on a patch of ice, takes 5 seconds to stop. What's the car's acceleration? Lots of stopping things happening here. All right, so there we go, number 5. So first the car moves like this, comes to a stop, so final velocity is 0. First the car is moving like this. Hey, wait a minute, that must mean the acceleration must be pointing this way. Let's do a VOVAT. VOVAT. Okay, we know the final velocity is going to be 0. What else do I know? It takes 5 seconds. 14 meters per second is how it's moving. I'm looking for the acceleration. So it takes 5 seconds. 14 meters per second is how fast it's moving, and I'm looking for the acceleration. I'm thinking v equals v naught plus at. So v minus v naught over t equals the acceleration. And plugging everything in, that's going to be 0 minus 14 divided by 5, which is my acceleration. So it's going to be 14 divided by 5, or negative 14 divided by 5. So it's going to be negative 2.8 meters per second squared. Boom. Is that right? Negative 2.8 meters per second squared. Yep. How far does it travel? Getting kind of repetitive now. So let's see, I'm going to use displacement equals the initial velocity times the time plus 1/2 at squared. Displacement is the initial velocity, which is 14, multiplied by time, which is 5, plus 1/2 times the acceleration, which I just found is 2.8. Negative 2.8, so careful, careful, careful. I'm going to plug all this in. Let's see, that's 25 times, whoop. So that's 25 times 0.5 times negative 2.8 plus 14 times 5, 35. I'm getting a displacement of 35 meters. Is that right? Is that right? 35 meters. Nailed it. All right, next up here we get a police find skid marks along... Sorry, skid marks 32 meters long on a highway showing where the car made an emergency stop. Assume the acceleration was 10 meters per second squared. I will, thanks. How fast was the car going? Was the car exceeding the 80 kilometer per hour speed limit? So 32 meters long and negative 10 meters per second squared. All right, let's do it over here. What number is this? 5, 6? What are we on? 6. So 32 meters long, so 6. And then we're also going to assume, so here we go again, boom, boom. First it's moving like this, acceleration is going to be pointing this way. This is my initial velocity, final velocity is 0. And we know the displacement is like that. So do a VOVAT, pretty sure the displacement was 32 meters, so I think it was negative 10 meters per second squared was the acceleration. We know the final velocity is 0, and I think the displacement was 32 meters. Let's double check that. Displacement is 32 meters, that's right. Okay, so I'm trying to find out what the initial velocity was. I'm thinking v squared equals v naught squared plus 2ad. So getting that initial velocity, that's going to be, let's see, this is 0, right? The final velocity is 0. So rearranging this, I'm going to get negative 2ad equals v naught. Take the square root of all that. You might think, oh no, That's the negative square root. I can't take a negative square root, but that's negative 2, remember, multiplied by negative 10, which is the acceleration, multiplied by 32, and those negatives are going to cancel out. So that's going to give me my initial velocity. So that's 2 times 10, which is 20 times 32. So 20 times 32, and I'm going to take the square root of all that and get about 25.3 meters per second. And that is my answer there. So let's see. 25.3, that's right. If you convert that, you'll get 91 kilometers per hour. So that sucker be speeding, yo. Oh, man. All right. Let's move on to number 7 now. It says a camera is accidentally dropped off the edge of the cliff. Oh, dropped off the edge of the cliff. That must mean then the initial velocity is equal to 0. And then 5 seconds later, it hits the bottom. How fast was it going before it hit? All right, let's do this. So I'm going to do this one is number 7. Right here, we got an object is dropped. This is just before it reaches the ground. Let's say this is the ground here. And we're trying to find out what the final velocity is. The initial velocity, though, is 0. We also got the acceleration, points down like that. There's a displacement here as well. So that'll be my displacement, like this. So we got vo, v, a, d, t. So we know the initial velocity is 0, negative 10 meters per second squared. This is a free fall problem. It's dropped in the air. We just need one more bit of information. I think that is the 5 seconds, right? 5 seconds later, yeah. 5 seconds later it takes to hit the ground. So 5 seconds later it takes to hit the ground. So this is 5 seconds. Let's see, what are we trying to find out? What's the final velocity, basically? So I'm going to use the final velocity equals the initial velocity plus the acceleration times the time. So the final velocity is equal to the initial velocity, which is 0, plus the acceleration, which is negative 10, multiplied by the time, which is 5. So the final velocity is going to be negative 10 times 5 is negative 50 meters per second. Boom, nailed it. And I'm pretty sure the next question is going to ask me about the displacement, because that's what they like you to do. Fill out the VOVAT. There you go, negative 50 or 49. That's the speed, because it's asking how fast. So it's just asking the speed. So the negative doesn't matter in this case. And they got 49, I got 50. That's because I used negative 10. They probably use 9.8. No biggie. That's fine. So let's see. How high is the cliff? So that's basically the displacement, because the rock falls, or the camera falls, the whole displacement there. So I'm going to use displacement equals v naught t plus 1/2 a t squared. And let's plug all this in. My initial velocity is 0, multiplied by the time, which is 5. 0 times 5 is 0, plus 1/2 times negative 10 times 5 again squared. So that's going to be 0 times 5 is 0, but then 5 squared is 25 times negative 10 times 1/2, which should be about negative 125 meters. And that's pretty much what we get here. 120, again, they probably use 9.8. We use 10. That's fine. That's close enough. Okay, moving on to 8. It says a toy rocket is shot straight up into the air at an initial speed of 45 meters per second. How long does it take to reach the highest point? And then how high does the rocket rise above the ground? So it's shot up into the air, and it's a rocket, so rockets generally tend to be shot up into the air from the ground. So let's see. Let's do this one. It's going to be 8 here. So we'll say the rocket starts here, it ends here, and so it is going to have some initial velocity because the rocket shoots up in the air. When it reaches its highest point, that'll be my final moment. So my initial moment is when it's being shot up in the air. My final moment is when it reaches its highest point. And the final moment at its highest point, the velocity is going to be 0. We also know the acceleration is going to point downward at negative 10 meters per second squared. And I'll do a displacement vector as well here, like that. So we got initial velocity, final velocity, acceleration, displacement, and time. We know the final velocity is 0. We know the acceleration is negative 10 meters per second squared. What else are we supposed to get here? 45 meters per second. So we're trying to find the time and then the displacement. So 45 meters per second is how fast it takes to launch into the air. We're trying to find the time. I'm thinking v equals v naught plus at. trying to find the time, so it's going to be the final velocity minus the initial velocity divided by the acceleration is equal to the time. So the final velocity is going to be 0 minus the initial velocity, which is 45 meters per second, divided by the acceleration, which is negative 10. So that means that the time is going to be 4.5 seconds about. Again, they might have used 9.8, which is okay. Next up, we want to find the displacement. Again, I like to use this for my displacement. V naught t plus 1/2 at squared. Now, plugging in for my displacement, initial velocity in this case is 45, multiplied by the time, which I just found out was 4.5, plus 1/2 times negative 10, 4.5 squared. Displacement should be 4.5 squared times 0.5 times negative 10 plus 45 times 4.5. 101, about 101 meters is the displacement. Is that the case? Do I get 4.5 and 101? 4.5, close enough. 101, close enough. Awesome, got it. Next up, number 9. Michelle threw a basketball straight up into the air. She let go at of the ball at 162 centimeters above the ground. The ball was timed to be at 1.26 seconds when it reached its highest point. And we want to find out what is the initial velocity of the basketball. So again, 162 centimeters and 1.26 seconds it took. This sounds familiar. This sounds familiar. Sounds like a throw the ball activity right there, right? So you got Michelle here, like you do. Just throw the ball up like that. It's going to be green. Green ball. There we go. Like that. So she throws it up. And there's it's going to be an acceleration, obviously, like that. She throws it up with some initial velocity. That's what we're trying to find out. Final velocity when it reaches the top, obviously, is going to be 0. We've also got displacement. Let's try and do a displacement right there. But then also, lastly, there's an initial height right here, which we'll talk about a little more a little bit later. Going to make a VOVAT. Oh, and again, this is going to be my initial moment. This is going to be my final moment. So at my final moment, the velocity is 0. Acceleration is negative 10 meters per second squared. 1.26 seconds and 162 centimeters above. So 1.62 meters. And then, oh crap, I just forgot it. So she let go of the ball. Oh, sorry, that's not right. The displacement's not 1.62. That's not right. That's the initial height. So the initial height is 1.62 meters above, but the time it takes is 1.26 seconds to reach the top. 1.26 seconds. And we're trying to find out what the initial velocity is. Let's see. I'm thinking final velocity equals the initial velocity. That's the acceleration times the time. Trying to find out the initial velocity. So it's going to be final velocity minus the acceleration times the time is equal to the initial velocity. So the final velocity is 0 minus the acceleration, which is negative 10, multiplied by the time, which is 1.26. That's going to be my initial velocity. So that is 12.6 meters per second. Boom, there's my initial velocity. And next up, so let's see, 12.6, is that right? 12.3, close enough. How high above the ground did the ball reach? So we got 940 centimeters. Remember, we're approximating at 10, so it might be a little bit different. So how high above the ground did the ball reach? Well, first off, I want to find out what the displacement is. Let's find out what the displacement is. So I think, again, we're going to use displacement equals the initial velocity times the time plus 1/2 at squared. So my displacement is my initial velocity, which I just found out was 12.6 meters per second times 1.26 seconds plus 1/2 times negative 10 times the time, which is 1.26 seconds squared. So I'm going to get a displacement of 12.6 times, or sorry, let's do 1.26 squared first times 0.5 times 10 times negative 10 plus 12.6 times 1.26. And I get 7.94 meters. Boom, nailed it, 7.94 meters. I got this thing. 7.94. Wait, what? 9.4. What? What? Oh, wait, that's right. 7.94. 7.94, which I just calculated. 7.94 is this. This is 7.94. But they want to know how high it is from the ground. So that's 7.94 plus the 1.62. So the total height, or we should say maximum height, is going to be h naught plus my displacement. So the maximum height is going to be h naught, which is 1.62, plus 7.94. So my maximum height is about 9.56 meters, or 956 centimeters. Let's see how that pans out. 940 centimeters, close enough. There you go. So again, it's a little bit off because we used -10. We approximated I approximated the -10, and there you go. Okay, so a lot of these explanations that I'm going to give you here are things you should write down as well. But I'm going to, for time's sake, I'm going to speak my explanations as I go. So it says which objects are at rest, and I got a position versus time graph. So objects that are at rest, well, let's see. The slope of a position time graph is what gives me the velocity. So objects at rest are going to be anything with a horizontal straight line, and that'd be A and E. All right, so which objects are accelerating on a position time graph? Objects that are accelerating are making curves. The only one that's making a curve is D. So D is going to be that one. Which objects are not moving? So not moving is the same thing as at rest, so that's also going to be A and E. Next up, which object or objects is changing their direction? Well, let's see. That would be changing a direction would be, well, so again, the slope of a velocity time graph, the slope of a position time graph gives me the velocity. So in this case, the velocity is constant. This one, it's at rest. This one, it's at rest. This velocity is constant. This is the only velocity that's accelerating, but it's actually, if you look at it, it's speeding up. It starts with a shallow slope and then gets a high positive slope. So none of these are changing direction. So actually none are changing direction. Which object is traveling the fastest? I don't really like this question. If I was to say the one that was constantly traveling the fastest, maybe B. But then again, oh yeah, that's not that. Because here D is moving pretty fast. I would say just about as fast as B. So okay, maybe B is traveling the fastest. Let's say. I would not ask you a question like this on the exam. That's a bad question. Not a bad question. It's a little unclear. If clarity ended up being an issue, please feel free to ask me during an exam. I'll clarify something like that. Which object is traveling the slowest? Well, probably the ones that are at rest. So A and E. And then lastly, which objects are moving in the same direction as object B? Object D is moving in the same direction as object B, because again, the tangent lines to the curve there, which are the instantaneous velocities, are always positive, so that means they're moving in the same direction. So I'm going to say D. There you go. All right, moving right along. Almost done. Let's use you. Okay, so it says, so here we got several students analyze a graph made from the following statements. Indicate whether the statements are correct or incorrect. Justify your answers by referring to specific features about the graph. Again, my justifying is going to be how I'm talking to you. So here we go. After 4 seconds, the rocket is moving in the negative direction, i.e. down. So here's 4 seconds, and we say, oh, the graph is going down, but I need to be careful. This is a velocity versus time graph. So it's a velocity versus time graph. So that means the velocity is positive, but now it's getting less positive. But it's still positive. And the velocity being positive, that means that it's still moving, well, in this case it's a rocket, so it's still moving up. Here it's moving up, it's moving up, it's moving up, it's moving up, it's moving up. But now this is the maximum moving up, the maximum amount that it moves up. This is the fastest it goes in the positive direction. and now it's slowing down in the positive direction, but it's still going in the positive direction. It doesn't start going in the negative direction until it moves past this 0 mark here into the negative velocity. So that is the reason why I'm going to say this is not correct, right? Because it is not moving in the negative direction after 4 seconds. It's actually still moving in the positive direction because we still got positive velocity. It's above this 0 mark. Let's make something to indicate where the 0 mark is. So here's my 0 mark, right? This is time. But here's my 0 mark, and it's all, the velocity is positive all throughout here. So the velocity is positive throughout, so it's not changing direction there. So that is definitely no. The rocket, next up, the rocket is traveling with a greater speed during the time interval from 0 to 1 second than the time interval from 1 to 4. So here's 0 to 1. The slope is bigger than from here 1 to 4. The slope is smaller. However, again, this is a velocity versus time graph. So velocity versus time graph, the slope is telling me about the acceleration, not the speed. Not the speed. So the slope, well, so the acceleration is smaller for here than it is for here, but the speed, it's saying the rocket is traveling with greater speed from 0 to 1. That's not true at all. The speed is 40 here, it's 60 here, it's 80 here, it's 100 here, meters per second. All those, right? So that's not true either. The speed is actually getting bigger from 1 to 4 seconds than it was from 0 to 1. All right. Next up, it says the rocket changes its direction after the 4 second. Well, again, that's similar to this question up here. It's not changing direction. It's actually just slowing down. So the acceleration is changing direction. We go from a positive slope to a negative slope. So the acceleration is changing direction, but the rocket itself changes direction. That's basically talking about the velocity. No, it's not changing direction there. During the time from 4 to 9 seconds, the rocket is moving in the positive direction up and slowing down. So from 4 to 9 seconds, is the rocket moving in the positive direction? Yes, it's got a positive velocity. It's above the origin there. So that's definitely true. Is it slowing down? Yeah, it's actually going. It's going from 100 to 80 to 60 to 40 to. It is actually slowing down. It's getting more negative or less positive. So yeah, actually this one's correct. All right, last one here. In 9 seconds, the rocket has returned to its initial starting position. So at 9 seconds, it's here, and that means the velocity at this point is 0. So the velocity at 9 seconds is 0, but is it back at its initial position? Not at all, right? Because this is a velocity versus time graph, and the velocity is the area under, the displacement is the area under a velocity time graph, and we got a bunch of positive displacement here. So this whole time, the object's been moving in the positive direction. No, it is not. Not even close. And you might have encountered this with the Khan Academy stuff, actually. But yeah, this is all positive displacement. So it's far, far, far away from the origin there. So actually, this one is also going to be no. So it's not back at its initial starting position, but it is back at rest. It's at rest at that moment. So there we go. There's that one. Again, I am moving fast, I know. So for this one here, it says we got graphs of velocity versus time again. And it says for the 6 second time interval shown, so this goes, both of them go up to 6 seconds, is the displacement of the object 1 in the upper graph. So displacement, is it greater than, less than, equal to, or less than the displacement of object 2? Well, let's see, it's a velocity versus time graph. And how do I get displacement from a velocity time graph? Well, displacement for a velocity time graph, so displacement for v versus t graph is the area under the graph. So that's a big idea there. In this area here, the question is, who's got the bigger area? The bigger positive area, and all this area is positive. So if you calculate all this, you should find you should find that object 2 has the bigger area. Object 2 has the bigger area, I think. I'm looking at this. Yeah, that's what it's looking like. So you could try calculating it for yourself. You should find object 2 has the bigger area. So the question is the displacement of object 1 greater than, equal to, or less than? Object 1 is less than the displacement of object 2. So this is going to be less than. And the reason why is because you would say to get the displacement on the velocity time graph, it's the area under the graph, and object 2's area is greater than object 1's area. There you go. That justifies it. Next up, it says Carmela and Desi leave a parking lot separately and drive west. Okay, they're driving west, but I'm actually going to call west positive just to make this easier for me here. It says they both start from rest. So they both start from rest. Desi leaves first traveling with an acceleration of 4 meters per second squared for the first 6 seconds. So this is all Desi here. And then she's driving and then drives at a constant velocity after 6 seconds. 2 seconds after Desi started, Carmela starts with an acceleration of 3 meters per second squared in west for 10 seconds and then moves at a constant velocity. Okay, so and now we're going to make a graph for the up to 6 from t equals 0 to 16 seconds when Desi leaves. So Desi leaves, let's see, Desi leaves at the beginning. I'm going to make Desi, this one, purple. So 4 meters per second squared for 6 seconds. So she starts at rest and goes at 4 meters per second squared for 6 seconds. So I want to try and find out what her final velocity is. So here's Desi. I'm going to use v equals v. Again, I'm moving fast here. I know what I'm doing. I know where I'm going. So don't think you're going to be moving this fast on this. So to get her final, I want to get her final velocity after 6 seconds. So the final velocity is going to be her initial velocity, which is 0, right? And I could write on a Vovat if I wanted to. Here's my Desi Vovat. Let's do that. Let's make a Desi Vovat. Vovat. So we know Desi's initial velocity is 0. She's accelerating at 4 meters per second squared. The acceleration is 6 seconds. So for Desi, we're going to get final velocity equals the initial velocity plus a times t. And let's plug in final velocity is 0 plus the acceleration, which is 4 times 6 seconds. So her final velocity is going to be 24 meters per second. And that's how fast she's going to be going when she then starts moving at a constant velocity. So at 6 seconds, so she starts at 0, but at 6 seconds, she's moving 24 meters per second. So I'm going to, yeah, sure, I'll throw out the ruler. Let's get all fancy here. Oh, and they also tell me, so just to, well, I'll make Desi purple and then Carmela another. So Desi's going to be purple, boom, like that. And now she's going to move at a constant velocity the rest of the time, all the way up to those 16 seconds, just like that. Now, and in fact, let's give Desi the purples. So there we go. Remember, west is positive. So Desi, 4 to 6 seconds. And then Carmela, I'm going to use yellow. 2 seconds after Desi started. All right, let's try this. So 2 seconds after Desi started, so now Carmela, again, starts from rest. So here's Carmela. And make her Vovat. Vovat. She is also starting from rest. She does it for 10 seconds. And she's accelerating at 3 meters per second squared for 10 seconds. So again, I think I'm going to use V equals V naught plus AT. V equals V naught, which is 0, plus the acceleration, which is 3, times her time, which is 10. So her final velocity is going to be 30 meters per second. So 30 meters per second, that's 10 seconds afterwards, so it's at 12 seconds there. Because remember, it's 10 seconds after she starts, which was 2 seconds later. All right. So 30 meters per second, boom, she's going to be here. And let's get our graph. There we go. Awesome. And now she's moving. There you go. Yeah, it should be a little bit above. That's all right. And there you go. So that's what the graphs look like. Pretty cool. Hopefully that helped. All right. I'm going to bed. Good night, everybody.